Hi, welcome back to the Shack. Unless you think this channel is about nothing but teletypes, here we have a few items that are not teletypes that we want to take a look at here on the bench today. These are some items that I got at a local Hamfest this weekend, and there's one more that we'll take a look at here in a moment. These are some DC milliampere meters and a coaxial transmit-receive switch. We're going to characterize one of these meters and learn how to do that, and we're going to tear down this transmit-receive switch and compare it with a homebrew TR switch that I made a couple of years ago. In addition, we'll look at one other item that I got at the Hamfest. This is the third item I got, and it is a traveling electronics repair case for tubes. And I got it mostly for the case because I have a significant number of tubes that I don't have a good place to store. But it in fact also has quite a few tubes in it. Now, you probably can't read the labels on these tubes, but most of them are series filament tubes or battery tubes that I'm not going to have a lot of use for. Like this guy here has a 1.5 volt filament, and I don't have a lot of use for that. And so those tubes I'll probably just take out of this box in order to make room for other tubes that I will have a use for. But there are some tubes in the box that are useful. There's a 12AT6 over there, some 12 SN7s, 6J6, 5Y3, some tubes that actually go in radios that I have. As you can see from the upside down tag there, I paid $30, actually less than that because I bought a number of items and got a discount. But paid $30 for the box with all the tubes, and I think I came out okay. But now let's take a look at the really interesting stuff. So these vintage meters I bought, as I said, to hopefully put on my Teletype current loop to measure the current on the loop. And I want to talk a little bit about buying vintage meters and characterizing vintage meters. And I'm by no means an expert in this, but I do have some tips I can pass along. One is, when you're looking at a vintage meter, how do you know if you're looking at a meter that stands a fair chance of working when you get it home? And there's a couple of simple things to look for, and they won't guarantee anything, but they will increase the chances that you take home a meter you can use. And one is, just pick the meter up and gently shake it. See how the needle is moving there? That's a good sign. There's two things that we're looking at here that are a good sign. One is that it moves freely, which tells us that it's not bound up and that the mechanism is not stuck. And two is, after it bounces, it returns to approximately the same place. And that tells us that not only is the mechanism free, but there's at least some sort of electrical action going on there. And there's another check you can do that's very easy to do if you have with you a shorting bar or an alligator clip or something like that. And that is to short the pins and look at the change in the bounce. So without this alligator clip shorting the studs on the back of the meter, when I shake it lightly, it's going, maybe plus or minus 30 milliamps there. If I short that pin and shake it a similar amount, it goes plus or minus 15 or 20 milliamps. And that's a good sign. That tells us that the inductor in the meter is not open. Now, some meters have more visible change than others when you do that, and some meters have more bounce than others, so it's not a foolproof test, but it does tell you that you stand a good chance of getting a meter you can use when you get home. Now, I didn't test either of these meters that way. I just picked them up and waved them a little bit. The other thing that you usually want to look at is, of course, surface finish. And this one, while it has this paint on it, it scrapes right off. And so hopefully I'll be able to clean this meter up and make it look reasonably nice. Now, this other meter has some issues that I knew when I picked it up, but I gambled on it. And I think it's an okay meter, but it's not going to be what I had wanted to use it for, which is okay. That's why I got two. Notice that it doesn't rest at 0. Now, that sometimes is a problem and sometimes isn't. You can often take the cover off of these meters, and there's a little adjust to change the resting point. This is a cheap meter. It doesn't have one of those. So, it doesn't 0, which means that it's not going to be completely accurate. It'll either have to be nonlinear in order to be accurate in the region where you care about it, or it's going to be off by, say, 7 or so milliamps. The other thing is this meter, and you can't really tell it just waving it like that, it has, well, I guess you can. It has a lot of bounce, and when I put it on a signal, it bounces all over the place, really more than is appropriate for the signal that I had thought about putting it on. because it changes with high frequency. So the other thing I want to do here is show how you, once you get one of these meters home, how you can characterize it. And be very careful when you do this, and recognize that when you try to characterize a vintage meter that you don't know anything about, that you run a real chance of blowing the meter, destroying it and making it not useful. And the reason for that is that these meters are sometimes extremely sensitive. Some of them have sensitivity down into the microamps or microvolts range, regardless of what the scale on the front of the meter says. Now, these are cheap meters. This one's a little nicer than the other one, but often the cheap meters have a little bit more robustness. But one of the things you want to know, for example, with a meter like this, is it actually a 200 milliampere meter? Or is it a meter with, say, 1 milliamp or 10 milliamp full scale that's going to require a shunt resistor? So let's take a look at that. To characterize one of these meters, you're going to need a current source and an ammeter. Now, of course, a current source can be produced from a voltage source, which most of us should have on our benches, and a known load, and an ammeter can be produced from a voltage meter and a known load. But in this case, what we're going to use is a multimeter with an ammeter function, a microammeter and milliammeter function, and a voltage source, which, as you can see, I've got dialed into 10 volts. And you can use any voltage for this. I'm using 10 volts because it makes the math easy, and this particular voltage source doesn't conveniently go down to 1 volt. What we want to find is the full scale current for this meter. That is, the current through this meter that causes it to go all the way to this rightmost line here. And we can do that in a number of ways. And as I mentioned before, you can blow up a meter doing this the wrong way. So we want to go about it very carefully. In particular, some of these meters have a full-scale current of as low as 1 microamp. You're unlikely to see anything less than that. In fact, you're unlikely to see anything probably less than about 10 or 15 microamps, but still. For a DC current meter of a low scale like this, it's actually not unlikely that there's an internal shunt in this meter and that it actually is direct reading. That is, if you pass 200 milliamperes through this meter, that it would indicate 200 milliamperes. But for large current meters, like a 20 amp or a 40 amp or a 50 amp meter, which you'll see, that's unlikely. And the reason for that is that the meter itself would have to be so beefy just to be able to pass that much current that it's much easier to put a shunt somewhere else in a part of your circuit that's already beefy and just run sensing wires up to your ammeter. But in this case, what we're going to do is we're going to start by putting about 1 microamp into this meter and see if the needle moves. If the needle does not move, then we'll start stepping our current up. So what I'm going to use here in order to do that is some discrete resistors. Now, you can use a potentiometer for this, but I need, for 1 microamp through this meter, I need a 10 megohm resistor, and I don't have a 10 meg potentiometer available. So what I've got instead is I have a few orders of magnitude of resistors here that we can put in this circuit in order to try to characterize this meter. So first, what we're going to do is we'll just go ahead and put this resistor in the circuit with just the ammeter and set it to microamps and make sure we see about the current that we expect to see. Be very careful when doing this because you can blow a fuse in your DMM and you can blow the coil in the meter if you do this wrong. So move carefully, pay attention to what you're doing, and be careful. So of course, in order to measure current, we have to be in line with the device that we're measuring. So first thing we're going to do here is we're going to go ahead and put this resistor in line across this voltage source with the meter in series. And what we should see here is we should see, well, see, we're seeing 4.5 volts dropping through this resistor. Which is not the current that we're looking for, but it shows us that we are in fact in line. See, if we go from the common here on the meter out to the resistor to the common on the power supply, and then from the positive on the power supply back into the meter. And with some digital multimeters, you'll have to pay attention to which direction you do this. With this one, I don't. I'm good in either direction. It'll just give me a negative current. So then the next thing we want to do is we want to switch this over to microamps and plug our lead into the microamp measurement. And see, we're getting a little less than 1 microamp here. This resistor is probably a little bit high, so we're getting a little less than 1 microamp. So seeing that we actually have a little less than 1 microamp flowing through this circuit, we can now put our meter in line and see if the needle moves on the meter. So now we're still showing less than 1 microamp, and in fact our needle is not moving. Nothing is happening here with our meter. So we can be fairly certain that this is not a 1 microamp meter. And so what we want to do next is we want to step up an order of magnitude and see if maybe it's more like 10 microamps. So here I have a 1 meg resistor that we'll put in the circuit. So we have 10 microamps reading on our digital meter and still no movement on this meter. So I'm going to step from there to 1 milliamp. Now be careful when you're doing this. If you touch these two probes together, that's going to be a dead short across your power supply. Now my power supply is current limited, but if your power supply in particular is not current limited, you want to be careful. And we can also blow our meter doing this. Speaking of, I need to switch into my milliamp range, which is the same socket on this multimeter, so if I were in the wrong range I would be okay. But many multimeters you'll have to switch sockets for multiple amperage ratings. Notice that the 10 amp is a separate socket. You may not be able to see that, but 10 amp is a separate socket on this meter because it has a different fuse. So we've got 10 milliamps here. I'm sorry, 1 milliamp here passing through this meter, and we still don't see any sort of deflection. So at this point I would say, this is probably a direct reading meter. But let's go ahead and jump from 1 milliamp to 10 milliamps rather than just getting crazy. Alright, there, I don't know if you could see, but the meter does move when I put the signal on there. In fact, the meter is now in here backwards, we can see. There we go. So we're getting a deflection actually of about 10 milliamps on the meter with the 10 milliamp load. Now it's not quite down to 0 here, but it goes up by about 10. Okay, so the last resistor I have here is 100 milliamp, and we should see it go to about half scale with 100 milliamp. And in fact we do. We see it go almost exactly to 100 milliamp, but we're only seeing about 90 milliamps here on the digital meter. Now these are 10% resistors, so probably this resistor again is a little bit high. So the other thing we've learned here is which of our leads is positive on the back of the meter and which is negative. So if you remember, our positive is coming through the meter, and so it's on this black lead right here. And so this is the black lead on the back of the meter, so this is our positive terminal on the meter right here. And you can even see someone has in the past scratched a little plus, it looks like, right there. So we've now characterized this meter, and we find that it is a direct reading 200 milliamp DC meter. So I can just put this directly in my teletype current loop, and it should read somewhere in the 60 milliamp range. It looks like it'll probably read closer to 70 because of where the 0 is falling here. And I don't know, I doubt this meter is adjustable for 0. It looks like it was sealed when it was put together. I should mention, and I didn't, that we just select these resistors using Ohm's law. We know we have a 10 volt voltage source, and so we can just use resistors of the in the 10 series, so 100 ohm, 1000 ohm, 10,000 ohm, etc., to produce the currents that we want. And you just use Ohm's law to calculate the current through the loop and then put your ammeter in that loop. The last thing I want to look at is this coaxial switch. Now, I did a blog post a number of years ago where I made a coaxial switch, and I called it a Dowkey style switch because that's where I was living at the time, colloquially people called pretty much any TR switch a Dowkey. And some people rightfully complained that it in fact is not a Dowkey style switch, whereas this, while it's not Dowkey branded, it's Wheelock Standards, manufactured by Signal Engineering and Manufacturing Company, is a Dowkey style of relay, more so than this is. And what this has inside is just a regular double pole, double throw ice cube relay, 115 volt ice cube relay with a 115 volt plug on it. And you hook the antenna here, a receiver here, and a transmitter here. And when it's not plugged in, or when there's no power on the plug rather, the receiver is hooked to the antenna. And when you put power on the plug, the transmitter is hooked to the antenna and the receiver is disconnected. So that's on one side of the double pole double throw relay, and on the other side are some extra terminals down here. Now these terminals are in parallel with the antenna because some vintage receivers use screw terminals rather than coaxial cable. But these simply go to the second set of contacts on the relay, and they can be used for muting your receiver when the transmitter throws in. So when the transmitter throws in, these two terminals are shorted together, which I use when I Drake 2B to mute the receiver so that I don't hear myself talking on the transmitter. But again, this is just an ice cube style relay in here. There's no attempt to preserve impedance. There's no particular attempt to shield. That's just hanging out inside there. And so it really is not a coaxial relay. It is simply a TR relay. What this is, on the other hand, is a coaxial relay. So let's crack this box open and take a look at it. Alright, here it is. We have the cover taken off of it. And one thing I want to mention before I go any farther is that these run on 115 volt line voltage. You see here it has a 115 60 hertz there marked on it. And they use two-prong plugs. And the reason they use two-prong plugs is that if you have a transmitter that's capable of keying a TR switch, it almost certainly has a two-prong plug on the back and not a three-prong plug. And in addition, that two-prong plug is not going to be isolated very likely from the line voltage. So you'll actually have line voltage going into this, which has a metal cabinet. Now, in the olden days, people considered this sort of okay. In fact, many times these vintage transmitters will have exposed terminals on the back that can have significant voltage on them. But these days, we sort of frown on this. Now, in most transmitters, your coaxial cable shield will in fact be bonded to the chassis of the transmitter. So when you have coax cable hooked to this box, you'll be bonding this chassis to the chassis of your transmitter, which should be at a neutral or safety ground. In fact, if you rewired the transmitter with a three-prong plug, which I always recommend, it'll be bonded to your safety ground, and so this will be grounded. But when there are no antennas, or I'm sorry, no radios hooked to this, the chassis will be floating and it has 115 volt line voltage in it. So bear that in mind and be careful with your vintage equipment. So this is what the construction of an actual coaxial relay looks like. And if you see, we have a sort of T-shaped path in here that goes from the antenna port to each of the transmit and receive ports down here, with a switch that moves a lever inside this shielded path back and forth when this solenoid operates. So when we put 115 volts on these two terminals, it pulls in this solenoid and switches from the receive side to the transmit side inside this shielded path. And that's how this is substantially different from the ice cube relay in this box, is that this, while it may not be 50 ohm impedance preserving, is at least a shielded path all the way through. And many times these were intended for high frequency use, and they can be impedance preserving. Many of the Dowkey branded switches actually are. I haven't looked up the model number here on this to see if it is or not, but in any case, it is isolated from the relay and shielded. And isolation from the relay is a nice property in that you avoid getting any sort of hum from your keying voltage into the signal line. So that's what a coaxial relay looks like, and that's why you might want one rather than a cheap and cheerful homebrew switch for your vintage setup. The one thing I'll point out about this particular relay is that if you notice, it does not have any terminals on it for the muting, and it does not have any extra terminals on the back on this relay that can be used for the muting. These are all these locked screws here that for some reason have been painted hot pink are mechanical screws that hold things together. None of them are additional terminals that might be used for muting. So in my case, I probably won't be able to use this between the CE and the Drake because I would like to have my automatic muting. But in other circumstances, or if I can find another set of terminals, and there may be one on the back of the central electronics to use for muting the Drake, this could be used in between a vintage transmitter and receiver. So I hope you enjoyed that look at some of my Hamfest finds and a little bit of a teardown and some characterization of a meter here in this video. And if you did, please hit like, click subscribe, and see what else will be coming up on the channel here. Thanks for watching.